Hola.
Pues ahora...
Espérate. Vale. Voy a hacerte presentar.
Vale, sí.
Gonzalo.
Mm.
Ya que si quieres. Vale, sí.
¿Me oís?
Hola Gonzalo, estoy ayudando a Flavio a conectarse. Ahora vengo por aquí.
Now is it fine, Gonzalo? Or good. How are you? Good, good. wow. Congratulations. Very nice. My first time as well for participating for presenting like in a school. So
Here we go.
So I think I forgot to connect my microphone and the internet. Thanks for one of the persons in the chat for pointing this to me. My apologies. I can't read again the speech, or just copy and paste so you don't miss anything. Okay, so before you start, Flavio, please allow me to explain some basic rules. So during the talk, the participants are free to ask questions. Mainly those who are, you can ask questions through via the chat, okay? Also in the YouTube channel. I will be paying attention to the YouTube channel, to the chat in the YouTube. And either me or someone of my collaborators will transmit the questions to the speaker, okay? Flavio in this case. At the end of the talk, or if it is something really important, we will interrupt the talk to transmit the questions. Okay, Flavio? That way you don't need to worry about any beeps or sounds that you hear during because the chat sometimes makes a sound, okay? So don't worry about that. If there is something really important, we will let you know. Okay, and also Flavio?
Just a question, the share screen is working, isn't it?
Yes, it's working, it's working.
Okay.
Now I will make it bigger to make it easier to read the slides. Okay, so I think that's it. So anything that, we planned 1 hour and a half for your first lecture, and it's
1 hour and a quarter, like.
a quarter, okay. So,
yeah.
But if at any point you feel tired or you want to make a rest, so you can stop, and we transmit the questions from the chat. Okay.
Okay.
Very good. So please, Flavio, feel free to start whenever you want. Thank you.
So let's start. Basically, during these classes, we are going to deal with two main topics concerning basically, on one hand, some classical aspects of the actions that are usually adopted in loop quantum gravity, is an immediate field. And on the other hand, the geometrical properties of non-Riemannian spacetimes. So spacetimes where some assumptions of general relativity are dropped off. This lecture, this specific one, is intended for being quite introductory. So my plan is to review some basic notions that will be useful also for the following classes. So we are going to review very, very basic topics. Of course, I take for granted some GR background, but anyway, if you have any doubts or questions, we see. So the idea is to review in this very first hour the general framework. So we will briefly discuss the theoretical context, fixed rotation, and doing calculation, some details. Friday is more for addressing the specific argument. So we are going to see the models, studying the kinematical and dynamical properties. Now, well, the title suggests, one key element we are going to talk about is the visibility field. So it makes sense to spend a little time on it, and just for explaining which are the context we are talking about. Actually, the visibility field is a little spoiler alert, because we are firstly going to discuss about the visibility parameter. So the visibility parameter is a parameter that is introduced in the Steiger formulation on general relativity. So in this sense, the very first topic we are going to talk about is the Steiger formulation. Please rely on the Steiger formulation GR. So in general terms, this is just an attempt to formulate GR like a sort of Young-Mills theory that is background independent. So the starting point of the entire machinery is just an observation with the equivalence principle that we always can fix in each point of the space-time manifold sort of local initial free. And in this sense, so we just imagine that we have a space-time manifold. We pick up a point and we can fix in this point a tangent space. And the idea is that we do a map that we call E, or just for simplicity. And this map brings us a Minkowski space-time that is span, let's say is, I mean, is a quite heuristically picture, so it's not intended to be very specific, just for getting the idea. And this intraspace space-time is spanned by an orthonormal basis that we call the Tedros field, in the sense that we can picture like this. Well, now this indices is an internal indices that denote the freedom that we have to rotate this orthonormal basis without altering, let's say, the structure of our microscopic space-time that we are locally describing the entire space-time. So we can say that by means of the Lorentz transformation, we rotate our set of tethers, but the space-time is basically the same. So the idea is that here we can describe a metric that let's call them GBE, like a projection on the microscopic space-time by means of these tethers. And when we perform a rotation, this basically means that we have let's call G prime metric that is given by microscopic space-time rotated by means of these rotated tethers. But we can see easily that by means of Lorentz transformation, these are the same. So this idea is implementing the formalism, and what we have obviously we have an additional degree of freedom due to this
possibility to perform rotations. So we expect also to have a connection related to these internal indices that we call the Lorentz, the spin connection, and it defines obviously the torsion tensor. That is one of the key elements we are talking about in the following. Is defined the Cartan structure equation, this one. And also it's defined the strength tensor, that's a sort of Riemann tensor, and when we deal with the metric formalism, but we will see this, so don't worry. So why all this? Because the idea in a staggered formulation is that we can add to the Palatini form of GR a term, this one, that is the Holst term, in such a way that we do not alter the classical prediction of this action. I mean, if we perform the variation of this action with respect to the spin connection, we eventually get the Lavida-Civita connection. So we plug back this form, this expression in the action, we see that by virtue of the Bianchi identity, the Holst term is identically vanishing. So this can be interesting to see. So during these classes, we are going to do quite a bit of calculation because, like I said, this is intended to be quite introductory. So this is one of the first elements that we are going to see. So let's observe the Holst action. The idea that we can introduce an operator that we define, let's say, BCD, where beta denote the fact that this Holst term is controlled by this parameter. That is the main topic of this lecture. This is the immunity parameter. And the idea is that we can define this operator P, beta, in the following way. So a couple of delta minus beta, the Lavida-Civita tensor in the internal indices. By means of this operator, we can rearrange the action of the Holst action in the following way. It's much simpler, let's say. So we introduce our operator. And now the idea, as we are going to perform a variation with respect to the spin connection, and since the variation of the Riemann tensor gives simply as the Palatini identity, we can switch off the terms by integration by parts, and we simply obtain when is one of the key elements when beta is different from plus or minus the imagined unity, the following four. So the variation S with respect to omega bring us to the following expressions, that is now the argument, the main argument is that this operator, which depends actually on beta, can put outside the derivation. Why? Because the beta is a parameter, it is a constant. So when beta is a constant, we can do this stuff and simply write in the following way. That is, we introduce a sort of new connection that we call omega, capital omega, that simply defined as the application of this operator on the variation with respect to the original spin connection. So we simply obtain this expression for the variation as a very. So we obtain these expressions. The fact that is that we have now only the variation with respect to this part. Don't worry about the indices, we fix later. The key point is that we have this part. And this part simply tell us that the connection has to be this Levita-Civita connection. So when we put back in the original action, we see that the host term is vanishing on half shell. I mean, where the equation of motion for the connection holds. Now, this is it isn't the only modification that we can perform to the Palatini action. We can enlarge our arguments to include also torsion, and this is called the Nian term, where we can see that we have this additional piece. And the main argument for doing this is the fact that if the host term is vanishing only on half shell, I mean, well, like I said, the classical equation for the connection holds, the Nian term is a boundary term. So we can neglect it at all, and we again we retain the same equation of like GR. Again, this argument holds when the beta is a parameter, is a constant, because if we imagine that we have a field like we are going to see in the next lectures, in this case we have beta that multiply our boundary term, and we can neglect it all because we eventually we will have a term that depends on the derivative of the beta field. So simply summing up, we have two types of extensions, that is the Holst and the Nian extensions of GR. In the first case, I mean the Holst case, we see that it's always is vanishing, but because of different arguments. In the Nian case, is a proper boundary terms, and we can neglect it. So why speaking about the immersive parameter? Where it enters and does it enter in the theory? The idea is that by means of this internal freedom we have to rotate the orthonormal basis, we can fix the direction of one of these vectors in such a way that is oriented like the normal of the hypersurfaces that we are splitting the space-time according to the classical ADM decomposition. In this way, we are frozen the boost sector of the Lorentz group, so we retain only SO3 that's locally equivalent to SU2 group. In this way, we have that the spin connection decomposes in two pieces. Pieces that is a special spin connection that is related to, I mean, to the three hypersurface we are slicing the space-time, and the other is a string curvature. This one is related to how this hypersurface is embedded in our space-time and how T varies. By means of these two pieces, we can combine them to form what finally is called the Steiger variable. That is this one. It's a proper connection for S2 groups, and its conjugate momentum that we call densitized triad. Now, I mean, we finished in the sense that we have a connection of the S2 group its conjugate momentum, and we can actually check that this couple of variables respect the so-called Gauss constraint that basically it takes count of the additional degrees of freedom of rotating the normal set we have seen before. Now, the importance of the Mirzi parameter relies on the fact that when we go on with the analysis, so we deal with some quantum aspects, we can actually evaluate the spectrum for the area operator. Now, we are not going to enter into the detail for the quantization, so just a brief sketch of that. And the main result is that the area, the spectrum of the area is quantized, where we have a sort of quantum number, but the key point that also it depends on the Mirzi parameter. So it makes sense to wonder about the physical meaning of this parameter. But well, we have different routes to this question, but the aspect that we are going to deal with is the fact that we can imagine to promote this parameter to a dynamical scalar field, and we see the consequence of it. Obviously, as I previously announced, to promote the parameter to be a dynamical field basically consists in the fact that the Holst or the Nian term are not anymore, let's say, a boundary term. So we just can imagine that the promotion of the Mirzi parameter to a field will bring us to the fact that we have an excitation of the metric-affine structure of the space-time, so torsion, and we'll see also no metricity. So in this sense, we are going to discuss also that the non-Riemann aspects of space-times, like I said, is a useful tools for the following classes also. So let's say we have two key elements. On one side, the metric tensor, it describes locally the causal properties of the space-times, and the affine connection. It's useful for defining covariant derivative and for comparing different tensorial quantities on different points of space-time. They are in principle independent objects, so we are going to see what it means. Now, like, as you already know, when we assume that the connection is a symmetry in its lower indices and is annihilate the metric, like metric compatibility, we have that the solution of the connection is just the Levita-Civita connection. So we can express the connection in terms of the metric, its derivative, once a local chart of coordinates has been fixed. But when we deal with non-Riemannian spacetimes, we have also two additional elements. I mean, curvature is the classic one, so we have the strength field for the connection. We have also torsion, that is the skew symmetric part of the connection. So we have now that this term is not vanishing, and we also the non-metricity, that is just the covariant derivative of the metric that now doesn't vanish. So let's review some elements and properties of these two kind of additional tensor that we have when we deal with metric-affine geometries. The first one is just the torsion, and we see that he carries 24 independent components because we have the antisymmetry in the last two indices. And we can imagine to split this tensor in its irreducible parts, so we can track the trace in the first and the third indices, that minus the trace in the first and the second indices. And the pseudo trace, that's just the completely antisymmetric part of the torsion tensor, and what is left. So a skew symmetric tensor Q that's antisymmetric into last indices and respect this and these properties. Now it makes sense to wonder about the geometrical meaning of torsion. And the basic fact that is in the presence of torsion, the infinitesimal parallelogram doesn't close. And we are going to see that in very detail. So just let's imagine that we have a couple of curves that we call gamma 2 and gamma 1. that are described by this type of affine parameterization, where lambda is our affine parameter. So we can imagine to define tangent vectors to this type of curves. We call them U, me and V, me. Now, what we are going to do is to parallel transport this type of vector along the other direction denoted by the other vector. So, for definition, parallel transported, we mean that the following holds. And the respective for the other type of vector. Now, for infinitesimal displacement along the gamma 1 and gamma 2 direction, we can write that the u prime vector, that is this vector, sort of, is simply given by u me plus a term that's simply the partial derivatives of the u vector contracted with the y direction. And similarly, the same thing holds for the v vector. So we have that v prime is simply given by v plus a term that is partial derivatives of v contracted with the x direction. So we have this is v prime. Now we have seen that the following and the following holds. So we can simply write that which implies that actually we can write the following. So we can repeat the same procedure for the v vector. We can obtain which again is equal minus the connection. Now, the idea is that we can subtract this one to this one. So we can rearrange the terms that we obtain in the following way. Look at this and this. So it brings us to the fact that we have u prime minus u, that is simply this term, and similarly we have that v prime minus v is simply this one. Now the idea is the fact that when we can rearrange this vector in the following composition, that is u prime plus u v plus u prime minus u plus v prime. Why I'm doing this? Because if we look at geometrical sense of these two vectors, we see that they can be identified with the diagonals of our open parallelogram, in the sense that we have v prime plus u, and is simply is diagonal, and the other one is this. So we see that when this difference is 0, we can imagine to close our parallelogram, so we have no torsion. But when we cannot do this, we have that the difference on the right-hand side of these two couples of equations simply give us the torsion. So in general, we can write that this difference is simply equal to minus the torsion contracted with the couple of vectors we have. So summing up, we have that when torsion is absent, we can close these two type of triangular But when we have torsion, we cannot do this. So infinitesimal parallelograms don't close. So we retain just a pentagon. But the fifth edge is given by the torsion. Now, the other elements that we have to deal with is the non-metricity. Like we did for the torsion tensor, we can perform the composition on the non-metricity tensor in its pieces. And again, we have two traces that are called the wave vector and the second trace that we are denoting with Q and P. And the last term is the traceless and symmetric part in the last two indices. Now, we saw that torsion is related to the fact that we cannot close parallelograms. So the next question is, what is the geometrical meaning of non-metricity? And we can see that in this case, non-metricity is related to the fact that the norm and the length of vectors are not preserved when they are parallel transported. So in the same way, we can imagine to take a curve that we call simply gamma, like before is given by this parametrization in terms of lambda. And we can imagine to take the inner product of two vectors that we call u and v, and we denote with theta the angle, but I mean, it's a heuristic picture, so it's the actual three-dimensional angle. And we can imagine that we know that in Riemann spacetimes, when we parallel transport, this inner product is conserved in the sense that it is zero. But when non-metricity is present, if we can expand this product, and we can write that x on the lambda plus the same term with u and v, which and we know that these terms are vanishing because the vectors are singularly parallel transport, but we have an additional term that stems out from the fact that we have here a metric that is not conserved anymore. So we have this additional piece. And this is not zero. And if we look at the definition, but on the first definition we gave about non-metricity, we see that this one is simply minus q e beta. So in this case, we can see that in general, the following holds, because if we take the v vector equal to the u vector, we see that the norm of a vector when is a parallel transport along a curve is not conserved. Now, a very simple example of this occurrence is when we deal with the so-called wild geometry. Wild geometry is characterized by the fact that we have a very simple expression for non-metricity that is given by the fact that we have the wave vector is simply 4 times the second trace, and we have the traceless part is identically vanishing. So in this case, the non-metricity simply taking the very simple form that is given by Q rho mini simply by P rho G mini. In this case, we can actually see that we can find a form that tells us how the length of the vector is changed during the parallel transportation. In fact, in this case, we can rewrite this expression in the following way. And this is actually a differential equation for the norm. So we can call the norm of the vector square like a sort of distances square, L square. And we can actually solve this type of equation. And we can see that finally, we can get the following expression. Let's say that's the length at the point, the final point x of our parallel transportation is simply given by a sort of initial length multiplied by this integral, that is simply the integral along the curve of the second trace of non-metricity. This is interesting because we can imagine what happens when we take a closed loop or a closed loop. So in this case, what we have? We have that our integral that is simply given by, we see this expression. We can re-express in the following way, like an integral along a closed curve gamma of the value vector, because we have seen that the following holds. So in this case, we retain this expression, but by the Stokes theorem, we can rearrange this integral in the following way, like an integral over the surface that the closed loop defines. And the interesting fact about this is the fact that in this case, this very expression is called homothetic curvature, and somehow related to another type of contraction that we can take in the Riemann tensor that we don't have in the usual case, and it's simply given by the contraction in the very first two indices. Because when we deal with metric-affine geometries, we have that the Riemann tensors is only antisymmetric in the last two indices, but not in the very first two indices. Now, let's say that we can imagine to take this vector in a very specific configuration where this vector q is proportional to the partial derivative of a scalar field. So in this case, we see that when we take a closed integral along a closed loop, because in this case q is proportional to a derivative of a scalar field, it actually is zero. So it's a sort of conservative field. It depends only on the final endpoint of our parallel transportation. So the fact that non-metricity changes the length of the vector can bring us to imagine also to seek for vectors that are actually preserved by this kind of parallel transportation. These are the so-called fixed length vectors. So it makes sense to seek for this type of vectors that are parallelly conserved. So let's imagine that we now are requiring that the following holds. So we have always the parallel transportation of vectors square, but now we are demanding that this is equal to 0. Now, the question is, what is the more general form that we can take for non-metricity in order that the following holds? The following holds if we sorry, we had a little disturb, but okay, now it's okay. So non-metricity, in this case, we can imagine to take in the following form. We can fix a coefficient for the first part and another coefficient for the second part. That's simply the symmetrization of the last two indices. We are neglecting a priori the last part because we know already that this is 0. Now, if we demand this, it simply means that we are demanding that the following holds, because we can always imagine that we can take this vector proportional to the same vector we are looking for. In this case, we eventually get that the following has to hold. So the Weyl trace has to be minus 1/2 of the second trace. And it's a very specific form that guarantees that the following is true. And we call them the fixed length vectors. Now, now we have torsion, no metricity, so we can wonder about what is the more general decomposition that we can realize for the connection. And it can be checked that the connection, a general connection, can be always decomposed in the following form, where we have the Levi-Civita part that we have already seen, plus two additional tensors that we call the contortional tensor and this formal tensor, that are related to the torsion and to the non-metricity. So how we can obtain these expressions for these two types of tensor? And this is also a very interesting fact to see when we are looking for very basic calculation. So we simply start with the fact that we have the definition of our non-metricity tensor that's simply given by minus the covariant derivatives in the indices rho of the metric G min. And if we expand this expression, we obtain this form. Now, the trick relies on the fact that we can imagine to realize a permutation on the indices, so we can do the following thing. And when we do this, we can write u min rho equal to minus the partial derivatives of the so we can follow the calculation. So we have and finally we do another permutation in the indices. So we do the following things. In this case, we obtain now the idea is that we can sum the second and the third equation and subtract to them the first one. So we sorry, we have a sort of problem. Okay. Wait for a moment. Okay. So when we do the following things, we have we have the third equation, the second one, and the very first one. So we can write the third one plus the second one minus the first one. In this case, if we perform the calculation, we simply obtain this expression. So minus QP min equal and in this piece, we can already recognize a sort of Levi-Civita part plus the symmetric part on the last two indices of the connection, plus two additional pieces that are the antisymmetric part of the connection in the last two indices. Now, we know in general that we can always decompose the connection in its symmetric part and in its antisymmetric part. So we can imagine to write the following thing, where now this is the torsion, 1/2 the torsion. So we can replace this term with the connection and with the torsion. So we obtain the Levi-Civita piece that we already see. Plus twice the connection and a combination of the torsion tensor. Now we can rearrange this expression, so we can solve for this part, multiply and contract it by a metric in order to delta to appear. And we finally get the following. We can see that this actually is the piece of the Levi-Civita connection plus what? 1/2 of this combination plus 1/2 a combination of this part of the nometricity tensor. And this is what we call the contortion tensor and this formal tension tensor. So finally, we get this expression for the connection. So in general, we expect three pieces. The ordinary one that we already know, an additional piece is due to the torsion, and a third one due to the nometricity. We observe that torsion is antisymmetric in its last two indices, but contortion is antisymmetric in the very first two indices. Meanwhile, this formal tensor is, it acquires the same symmetries of the nometricity, like we can see here. So it's always symmetric in the last two indices. Now, when we deal with metric-affine geometries, a very, very important issue that we have to talk about is the so-called projective transformation. I think also Adria is going to talk about that, so let's sketch that so in order to make more plain possible the following lectures. Is a transformation that we can perform on the affine connection, and it simply relies on a shift due to a vector degree that we call psi. We can see by simple calculation that in this case, the Riemann tensor is acquired this additional piece, but in the way that the Ricci tensor is left unchanged. So we can claim that is a sort of gauge symmetry for the general relativity when it is formulated in the Palatini formalism. But the physical quote meaning of this transformation is related to the fact that we can see it like a sort of reparametrization, the affine parameter that we are using to describe the curve along which we are performing autoparallel transportation. So we can actually check that this result holds. So let's imagine that we are starting with a curve gamma that is parameterized by the parameter lambda, and that we are calling is an autoparallel curve in the sense that it is not a geodesic, but is an autoparallel curve because it's defined by the entire connection gamma. When we perform a projective transformation, so we are displacing the connection by this additional piece, we can see that the right-hand side of this equation is not vanishing. So we can wonder about how can we reabsorb this additional term by means of reparameterization on the parameter lambda. And the idea is that we can, we can define a new parameter S that we call S of lambda in such a way that we can define now the derivatives with respect to this additional parameter. And we can see that we can always find a suitable expression for this parameter that is related basically to the integration on this function f along the curve, such a way that this term can be made vanishing. So the physical mean, let's say, that we have sort of an additional symmetries in the fine autoparallel curve that is related to this possibility to perform projective transformation. Now, a funny fact about projective transformation is the fact that we can use it also for make vanishing one of the vector we have at our disposal and define the torsion and endometricity components. So we can see the transformation rules for the trace, the second trace, or the axial part of the torsion. And what we are going to see in the last very few minutes is the fact that by means of a projective transformation, we can always find a connection that is called volume-preserving connection. I mean, because since in general, in the presence of endometricity, we have that the metric is not annihilated by the covariant derivative, it means also that the Levi-Civita tensor is not covariantly conserved by our operator nabla. But actually, it depends on the value vector. So in order to see that, let's just imagine that we have a connection that we call nabla simply gamma. So we have a Levi-Civita tensor, and this is defined obviously like the determinant of our metric times the Levi-Civita symbol. So in this case, we can expand this form to obtain plus all the terms that it contains the connection. So we have gamma lambda contracted with in the first indices of the symbol and so on. We have in this case, since when a couple of indices, let's call them mi e and mi j are equal, this term is vanishing, we can just select the indices in the following way, just for example. So in this case, what we obtain is obviously this now is a symbol, so we can bring outside the partial derivative operation. So we finish with the following form. So in this case, what do we see? We see that we can collect all the terms, so rewrite the covariant derivative of the Levi-Civita tensor in the following way. And now we know that by means of the previously seen decomposition, we know now that this trace of the connection is simply given by the trace, let's say, of the Levi-Civita part that is equal just to this piece with the opposite sign. So we have plus what the contraction of the contortion tensor plus the contraction of this formal tension. But we have said that this tensor is antisymmetric in the very first two indices, so it is 0, and we are left with this piece that is simply 1/2 of the Weyl vector. So finally, we simply obtain that these two pieces cancel out, and we have just this piece of the Weyl vector. So we can imagine to fix a projective transformation, and we can see here. So we can imagine to fix this vector in order that the transform Weyl vector is simply vanishing. So the Levi-Civita tensor is covariantly conserved by our covariant derivative operation. Now, this I see that this concludes the overview about the notations, the main topics we are going to talk about Friday. And just let me say that if you want, we can prove a couple of expressions that are related to this type of decomposition we are seeing. For example, you can try to see how you can decompose the Ricci scalar when for simplicity, you can neglect the non-metricity. So you can just retain the torsion components. You can check that the Ricci scalar decompose in the following way. Now, the hint is to use the decomposition, the connection, and see how the Riemann tensor is expressed in terms of the Levi-Civita pieces plus the other pieces. Another interesting expression that we can check is the fact that, like I said before, now in general metric-affine context, the Riemann tensor is not symmetric, antisymmetric in its two first indices. So now we expect that we can extract the symmetric part, and we can check that this part is equal to, let's say, to the non-metricity contribution to the Metric-Affine geometry. Here, the hint is to consider the commutator of the covariant derivatives acting on the metric G mu nu. So, Gonzalo, I think that we all, more or less, we're finished about this part.
You are now unmuted.
Okay, so thank you so much, Flavio, for your talk. We have some questions. In particular, David Benisti. David, do you want to ask the question directly to him, just in case you want to have some clarifications?
Yes, thank you very much. I mean, it was very interesting and very clear. I wanted to ask, when you mentioned like metric-affine connection, call this like gauge field or gauge symmetry inside.
Yeah, when I was speaking about Ashtager variables.
Okay. Okay. So can you repeat why you call this like a gauge field? I mean, how it's related to gauge symmetry or?
Okay. See, it's quite okay. So the very first slide.
Well, I think it was a bit later, but okay. Yes.
Okay. Here, no. Yes, the key element is the fact that we have this type of constraint, basically. That is called Gauss constraint, and it takes care of the additional freedom that we have to rotate our variables generally. And gauge fields, I mean, it's a sort of formulation of GR in terms of, in such a way that it resembles much we can a sort of Young's theory. As the main motivation that brings us to do this type of variables. I mean, it's not
exactly equal to a gauge theory of like you have, I know, QCD, stuff like this.
Yeah, but you have also like the connection to, I mean, you can define some gauge theory of gravity with respect, I mean,
sorry,
if you use
can you repeat that?
If you call like some gauge theory of gravity, not for instance for QCD or some other variables, I mean, if you use like one from the variables in gravity is a gauge field.
I mean, there is a trick in the sense that, like I said before, in order to do this, we fix the gauge. So we oriented the tetrad field in such a way that we can frozen the boost sector, the Lorentz group. In general, this is not always, but I mean, actually, nowadays, these are a bit old way to this kind of this approach a little bit old, because in general we prefer to not fix the gauge at all to see what happens. And in this case, the analysis is a bit more complicated, so it's not so easy to identify the connection and identify it right. So just take this like a sort of heuristical picture about we can reformulate GR, because the key element of GR, I mean, GR is a constraint theory, no? Because when we perform the EDM decomposition, we have that scalar constraint, the supermomentum constraint, the weakly vanishing on the upper surface, the constraint defined. So the analysis is a bit more complicated, but in general, it would be preferable to not fix the gauge and deal with second type constraints and so on. So I know it can be a little misguiding, because when we think about gauge theory, we think QCD, but it's a case, but it isn't the case. So
thank you very much. Thank you.
You are now
Okay, so Flavio, there is another question. Well, there are two questions. Abhishek Dusoi is asking if there is a review of paper summarizing this lecture somewhere. Or you can recommend some literature.
By a few days, I hope Gonzalo, our draft is going to appear. So in this sense, yes.
Okay, there will be something,
It will be
yes.
very soon.
My fault. Okay, and then there is another question by...
No, let me finish. Otherwise, you can check there is a PhD thesis about a guy in Greece that's called Iosifidis. And you can find quite a lot of these things.
Okay, we will provide the link in a while. So Albert is asking if one can construct a gravity model with non-metricity only, with no curvature.
Yes, of course. Actually, we can construct two types of theory, where we have only torsion on only non-metricity, or torsion on metricity and not curvature. They are called respectively teleparallel gravity, symmetric teleparallel gravity, or generalized symmetric teleparallel gravity. So in this case, you have to implement the constraint that the curvature is vanishing, but you can demonstrate that at least when you adopt a linear expression for the action, so just retain a type of combination of torsion and metricity, the two formulations are equivalent up to a boundary terms. The things are slightly different when you take a sort of generalization like FR theories in this case also.
Okay,
So,
and we have another question by Adria Delhomme, but I think that he should ask the question directly. Adria, can you open the microphone? Is Adria here? Well, he's not. Okay, the question is regarding the solution to the spin connection, equations with the Holtz term. So he has questions about that. So Adrian, you should have a microphone at the bottom below, at the bottom of the page, or maybe you.
Okay.
Okay.
So. So you end up this Covalent derivative d mu is exactly what? So you have variation with respect to omega gives us d mu or something related to the real line fields equals to 0.
yes.
This d mu, what is it exactly?
This d mu is defined with respect to the here. You see?
Okay.
It takes care of the additional indices that we have. This one, no? The internal indices of rotation.
Okay.
I mean, I omitted some calculation here because it can be quite lengthy, but the main property is this one. So when we vary the strength field that is defined here, we obtain a sort of generalization of the Palatine identity in terms of the spin connection. If we take into account the fact that the spin connection in general is antisymmetric on its internal indices, and the fact that we have defined the operator P, A, B, C, D, that is also antisymmetric in its indices, we can perform some switches, some integration by part, and rearrange all the variation in the way I showed you before. So in this way. And let me repeat that the fact that this operator is linear, it's invertible, is inversive, there is exists. I didn't calculate it explicitly, but if you want, I can show you. So the fact that we can bring it outside the unit of operation, so we can find a new variation, and the point is that the variation with respect to omega or another, let's say, connection that are related by an operator that is linear and has an inverse, it's basically the same. So we can just retain this part of the variation, and it defines the Lagrangian connection.
Okay, so the thing is that I would say that, I mean, because there is a lot of confusion with the nearby fields, and some people, for example, some people call this condition that the covariant derivative of the nearby is zero as a tetra postulate, but that is something that is an identity indeed. And I am always confused with the vocabulary. I don't expect that. Maybe I'm confused with the equation because I don't remember exactly how is the identity, but that.
I got your point. Actually, this is more. It's clear when we deal with the metric and the connection formalism. Doing this calculation, or use the external forms, or doing for components quite. It's not very clear. So don't worry about that, because Friday I'm going to use some calculation in the magic formalism, so it will be more clear.
Okay, or maybe we can discuss it.
Yeah, you're here.
Okay, thank you.
Thank you, Andrea, for your question. So there are no questions on the YouTube chat. So and here I don't see any other questions. So Flavio, thank you very much for your talk, your lecture, and we hope to see you when? Friday again?
Friday afternoon.
Very good. Don't miss his talk. You will learn a lot. Okay, thank you.
Bye.
Bye. So we will have now a short break for 15 minutes, and then we will come with our next speaker, who is already around here, Euclides. I saw him here before. I don't see. Yes, he's on the chat. Okay. So Euclides, remember. Okay, turn on your microphone. Is everything okay from your side? Are you already ready?
Well, I don't know how to use this. I just use once.
Yeah, no. So we have a small break, and we will make you a presenter, so you will see the button to upload your talk and all that. Okay, just in a few minutes. Okay.
Nice.
So very good. We will get back to you in a second. Okay. Now we have a short break. Thank you.
You are now muted.
Oops.
are now unmuted.
Okay, Euclides, are you there?
Yes.
Okay, very good. So you want to upload your talk, so we start with the
Let me see
session.
if I can do that. Let me share the screen.
Okay.
Okay.
So
Okay, let me take the full screen.
okay, right now I'm here. You're sharing. Oops, this is not what I wanted to do. This should be bigger. Oops. Why am I so big?
Okay, can you see it?
Yes, now I can see it. Yes,
Okay.
perfect.
So, is that working? Because I think I used this big button before, this blue button, and I think my presentation there was some holes, but it's working.
Yes, it's working. From here, I can see it clearly, and also on YouTube, it's also clear.
Okay, nice.
Okay.
Great.
So it is time to start. So our next speaker is Euclides Silva, who is speaking from the Universidade Federal do Cariri in Ceará, Brazil. And he is going to tell us about Randers-Finsler spacetime, symmetries and fields. So whenever you want, Euclides, you can start.
Okay. Thank you, Gonçalo, for the kind
Euclides, you are not sharing your camera, so because you didn't press the final button, so.
Oh, yes.
Okay, yeah, yes, okay. No, you're sharing your screen now.
Now it's fine.
Okay, very good, perfect. I think.
Okay, can you see me now?
Yes, but let me.
Yes.
There is a small visualization problem here from my side. I have to make you smaller. Okay, much better now. Oh, very good. So now we can see you. Yes, you can start, please. Go ahead.
Okay, so thank you, Gonçalo, for the kind invitation, and thank you all the organizers for this very great meeting. So I'd like to say hi, everyone. I think there's a lot of people from all around the world. So here in Brazil, it's early morning, but maybe it's not so early in other parts. So it's a pleasure. My name, as Gonçalo said, is Euclides, and I'm from Universidade Federal do Cariri. It's in Brazil, okay. And today I want to talk to you about symmetries and fields in Finsler spacetimes. Okay, so it's a little bit different from the usual Riemann-Cartan or Weil-Cartan spacetimes, but I think it's interesting to discuss. Okay, so this is outline from our presentation today. We make a very brief review on what is Finsler spacetime and his main geometric and physical properties. Then we skipped to a proposal. Actually, it's a proposal how to define fields in this in these Finsler spacetimes. And then we move to how to define gravitational dynamics on these spacetimes. Okay, so I think you have this question in your mind right now. So where is Cariri? Where is Ceará? Okay. So here is Brazil. I think you all know South America. So right here is Rio de Janeiro. Okay. So I lived here in Ceará. Ceará, it's a state from Brazil. It's in the northeast of Brazil. Okay, so it's really near. It's closer uh, to Europe and to Africa right here. So I think South Africa it's around here. Okay, so Ceará it's almost in the equator line, so it's in the same line of, I would say, Congo, if you like, and it's near from Paraíba. Paraíba it's the university from which Albert will present you. I think today, not sure, but if you have some, in order to have some unities, some scale. So from Fortaleza in Cariri, Cariri it's the south of Ceará. It's a region where lived these Cariri people. It's a Native American people. There is very few of them, so we don't know for sure what these words means, Cariri and Ceará. But Cariri it's in the south of Ceará. Okay, so to have a scale from Fortaleza to Rio de Janeiro or São Paulo, the biggest cities in Brazil, it's about 3 hours by flight. So, and the same for Amazon here. Here is Amazon, so we hear it's very different from Amazon. Okay. Okay, so let's go to the to the main topic. What is Finsler spacetime? Okay, so a Finsler spacetime it's a very interesting topic because what changes to define a Finsler spacetime is that you consider a different Finsler interval, a different definition of the interval in spacetime. So let's consider a spacetime here, M. Take a point in this spacetime, X, and consider a curve, a path here. So we can consider, for example, a word line. Okay, so you have this x dot. Okay, so in Finsler spacetime, this infinitesimal interval is measured using this smooth but not necessarily quadratic function of the point and the direction. Okay, so this condition it's very very general, and this is okay. So in Riemann geometry, the Finsler function is just a quadratic. It's measured using this quadratic form here. So in Finsler in Riemann geometry, the Finsler or pseudo Riemann geometry, the Finsler function is actually is quadratic in the velocities or in the direction. Okay, so in Finsler geometry, we may have non-quadratic functions of this velocity or this direction. Okay, so Finsler geometry, it's interesting topic also because you can here it's a sketch from the space-time, okay, but you can define these fibers, these tangent vectors in each point, this tangent space in each point define some fibers, and so you can define this fiber bundle here. Okay, so what's interesting also in Finsler geometry is that Finsler geometry it's a geometry not actually for the base space M, but actually for the tangent bundle. Let's see how it works. So if you consider here the base space, which is in our case the space-time, and you define these fibers, so you define this lift from the base space into the tangent bundle, okay? And the tangent bundle itself, you can define some coordinates there. So you can take a point in the tangent bundle and consider the position of the base space and this fiber, a point in this fiber. In other words, for velocity or the direction in this tangent space here. Okay, so you have this tangent bundle. It's a kind of a Lagrangian configuration space, right? So in this tangent bundle, you can define a metric, which is a really different metric from the Riemannian metric or pseudo-Riemannian metric in our case, because it's a metric defined here in the tangent bundle. So it depends both on the position and on the direction. And this metric, it's called Finsler metric. How can you define this? You just take this Finsler function, okay, this arbitrary Finsler function, u squared, and then you take this Hessian. So this Hessian is symmetric, so is symmetric this tensor here, okay, and in the usual pseudo-Riemannian geometry, this f square is quadratic in the velocities. So this is actually constant or depends only on the position, the x. Okay, so in general, the Finsler metric depends not only on the position but also on the direction. So Finsler metric, it's a very interesting object here because in some sense it can encodes all the information about the anisotropy, the local anisotropy of this geometry into this very fundamental tensor. Okay, so as I said, this metric can be actually better defined on the tangent bundle. Okay, but in order to do that, you actually have to consider the tangent bundle. In other words, you have to take a point here, x, uplift here to the tangent bundle. So you have this x and x dot. Make some variations here. So consider the tangent space in this tangent bundle point. So you consider actually the tangent bundle, okay? And the metric using this the basis, you have this double number of coordinates. You have this variation for the position and variation also for the velocities. Okay, so this is a metric it's a local metric for the tangent bundle. Okay. All right. So, but to define tensors, you have to define vectors, basis vectors, right? Or at least to take these components.
You are now muted.
In some specific basis, okay? So a very usual basis in Finsler geometry is this Sasaki lift here, where you define some orthogonal bases here. So you consider a variation in the position and a variation in the velocity in the tangent bundle. Okay, so to ensure that these base vectors are orthogonal, so you have to consider this tangent vector here, but this tangent vector is actually only here in the tangent space. Okay, so you have to define this nonlinear connection in order to ensure that this vector is everywhere orthogonal to that vector here. Okay? So using this tensor here, it's called nonlinear connection. So you can define, for example, these Christoffel symbols using the Finsler connection. So it's a Christoffel symbol, but it's not a connection. Okay? So to define a connection, it takes a little bit more in Finsler geometry. Another very interesting object is the so-called Cartan tensor. The Cartan tensor is the derivative of the Finsler metric with respect to the velocity here. Okay, so it's interesting because if you consider the pseudo-Riemannian metric, the pseudo-Riemannian metric does not depend on the velocity, right? So in pseudo-Riemannian metric, this Cartan tensor is zero identically. So this is a tensor who has the signature of this Finsler geometry nature. Okay. So out of these Christoffel symbols and this Cartan tensor, you can define this nonlinear connection here, this n, which is the same n used here. And it's called nonlinear connection because you contract the second term here, you contract this Cartan tensor with the Christoffel symbol, and you have this quadratic or nonlinear piece here. Okay. So far, we just defined this basis, this orthogonal basis here in the tangent bundle. Okay. So there's some duality here. So you have this variation only on the position here, and you have this dual basis here. And so you have this vector here and this dual basis right here. And this dual basis is also defined using this nonlinear connection. Okay. Okay, so far we just defined this basis and the dual basis for the tangent bundle. But how to define a connection on the tangent bundle? So what if you want to define 2 points here in the tangent bundle and try to connect them? So you have to define this connection one form here, right? But the point is the connection one form is defined on the tangent bundle, so it has this usual piece here, which we call the horizontal connection. But you also has this connection along these fibers, okay, along these velocities. So you have this kind of vertical. It's called vertical connection. Okay. You can also define this connection with respect to the metric. So there is some relation to the connection to the metric. You just consider this covariant derivative of the metric. And for example, this horizontal part, you can define this no metricity tensor. Okay, so you have a lot of different choice you may do, you may take in order to define these connections on Finsler space-time, just you do in usual pseudo-Riemann space-time. Okay. So a very interesting choice is made when you consider that this horizontal no metricity tensor is 0, and so you consider this connection having this piece here, which is the horizontal connection, and you have also this vertical connection, which acts only on the fibers. Okay, so this vertical piece here is actually this Cartan tensor, the derivative of the Finsler metric with respect to the velocity. And this horizontal connection here, which is used to translate, to transport, to parallel transport the vector in the base space, it's called the Cartan connection, okay, which is built using this Christoffel symbol and contractions of the metric, the Finsler metric, the Cartan connection, and also this nonlinear connection. So, in other words, to define a connection in the tangent bundle, which is horizontally compatible with the Finsler metric, you have to add some terms to the usual Levi-Civita connection, which are built using the Finsler function, the Cartan connection, and this nonlinear connection. Okay. So what we're gonna do is use this geometric framework to study some physics in these space-times, okay? Finsler space-times. So there's some proposals of Finsler space-times, for example, in the standard model extension, which is Lorentz violating effective field theories to describe how the Lorentz symmetry is broken by background vectors. So you have this you have some Finsler-based function, which is they have some perturbative characters here. For example, for a fermion, you can have this pseudo-Riemannian piece here, okay, and also this linear piece here and this quadratic piece here. This piece here we're gonna see, it's called this renders spacetime, okay, and this other piece here, it's called this bipartite spacetime, okay. So you have background vectors here, A mu and S mu, which are background vectors in this spacetime, which breaks or violates locally or if the spacetime is flat, also globally, the Lorentz symmetry. Okay, so here's for example, this S mu is a symmetric tensor, so it can be defined, for example, using another background vector, for example, this B mu. Okay, so this is a Finsler structure, a Finsler function for the spacetime, which is derived from this effective field theory here. Okay, so the renders spacetime is actually a little bit old, so it's from 1941, and you have this perturbative correction of the spacetime, which provides a preferred direction. And this preferred direction is given by this A mu vector right here. Okay? So you can think of, you have this, your space-time, you have now this point here, x, you have this velocity, you have a particle, and his word line here, and you have this background vector, B mu. And the interaction of this particle with this background vector and the gravity can be unified in the Finsler geometry. That's the point. Okay, so using this Finsler function here, which is renders Finsler function, we can you can calculate this Finsler metric, the renders metric, and it's interesting because the renders metric has the usual pseudo-Riemannian metric here, which is locally Lorentz invariant. but you have this factor multiplying here, okay? And you also have some corrections to the usual pseudo-Riemannian metric, which depends on the velocities here. So you have a metric which depends explicitly on the velocities. And you have also these background vectors. So in some way, the Finsler or the renders metric encodes not only the curvature and the geometric structure given by pseudo-Riemannian spacetimes, but also it encodes these background vectors also. Okay? So this u mu, it's the Lorentz invariant for velocity. Okay? So how does a particle feel this Finsler geometry? So if you consider that the Lagrangian for a particle is his mass times the interval, so now this canonical momentum, it's modified by this background vector. So you can say that the energy, momentum, and the dispersion relations are modified by this background vector. Okay? But if you want to consider that background vector is encoding into the geometry, maybe we can see some hidden symmetries, which is not obviously in base space, but you can see this in the tangent space. Okay, so for example, if you consider this canonical momentum here, and if you consider his dual component here using the Finsler metric, it turns out that this momentum is not just the mass times the force velocity, but it's divided by the Finsler function. And if you expand this Finsler function, you see that the relation between the renders or the Finsler momentum to the usual local Lorentz invariant momentum is given by these non-local powers of the momentum here. Okay, so this is a very interesting result. And also, if you consider that the dispersion relations is calculated or defined using this Finsler metric here, so you may have some non-quadratic dispersion relations, okay? But if you adopt, for example, this Cartan connection, which is compatible with the metric, so this relation is actually preserved when you move from a point A to a point B in the space-time. In other words, we are seeing some symmetry here, some Casimir-like operators here, okay, for the momentum, provided that you see these operators using this metric, the Finsler metric, in the Finsler connection. So we can see some hidden symmetries in this space-time, which is the space-time is breaking locally the Lorentz symmetry, okay? But we can define some deformed Lorentz symmetry, which is preserved by the Finsler metric and the Finsler connection. Okay? Let's see how we can define these hidden symmetries. We can define this Finsler-Killing equation. Okay, so we define the Lie derivative of the metric by considering these horizontal derivatives and also the horizontal derivatives of this Lie vector. But you have also to consider this additional term here, which it's a contraction of this Cartan tensor and this Lie vector. Okay? So if there is some symmetry in the space-time, so this Lie derivative at 0, and so you vanish here this equation, and you end up with a very interesting equation, which is very similar to the Kinley equation in the pseudo-Riemannian spacetimes, but you have also this term here. Okay, nice. Okay, let's consider an actual transformation, what is called the particle transformation. What is a particle transformation? It's an active transformation where you are considering some symmetries where the particle is moving along the space-time. So if you do so, this killing direction can be seen as proportional. It's actually orthogonal to the four velocity. So this term here vanishes, and so we just end up with this seems very useful, or it seems the usual Killing equation. But you have to consider here that this connection here is not the Levi-Civita connection. You are using here the Cartan connection. We are using this Cartan connection here to define this horizontal derivative here. Okay, so in this equation 17 already has some Finslerian corrections to the usual Killian equation. Okay, so let's see how this symmetries works. If the base spacetime is flat, I mean, if this base spacetime is only the Minkowski spacetime, for example, so you have this, you have some kind of global symmetry going on here. So, so you have this translation generator here. Okay, and you can also have some, which is solution of 17. Okay, so another solution of 17 is if you consider a kind of Lorentz or pseudo rotation, Lorentz transformation, okay, which is this omega whole nu, and this omega whole nu satisfy these equations provided that it is antisymmetric. But you can write these intakes using this Finsler metric instead of this pseudo-Riemannian metric. If you do so, now this rotation generator have this background metric here, but also depends on this background tensors here. This S min U tensor here is the bipartite tensor, but you also can have these renders corrections here. So what I'm doing here, I'm trying to define some solutions of the 17 equations, which provide some symmetries for the spacetime. And what I'm saying is that in Finsler spacetime, for a flat spacetime metric, pseudometric, you will still have some modified or deformed Lorentz symmetry, okay, which satisfy this equation here, and which encodes all the information about the background tensors here. Okay, so in some sense, this is a deformed Lorentz symmetry, which, using this Finsler metric, encodes all these backgrounds Lorentz violating terms tensor here in the deformed generators. Okay, so you can also modify the generators for G min U. Okay, so for this tensor, it's you just replace here, And the algebra, it's a very interesting topic here, because if you consider P nu and P nu, and they are defined by these derivatives, even though there is no curvature for the base space is Minkowski, but now you have this this connection, we are using Cartan connection, so you still have some direction dependence here. So you have some curvature, which comes not from the position, but from the direction. So in this case, we are using the momentum, the four momentum. So the commutator between two momentum is proportional to also the momentum. So you have a deformed algebra for this Finsler spacetime, at least for flats base spacetime. Okay? So some of these results were actually published 2 years ago by me and two collaborators from also Ceará, Roberto Maluf and Carlos Almeida, and there's additional details there. Okay? So I would like to move on to Finsler fields because we also had some tricks here. Okay. So far, we just treated the particle, but how can we deal with fields in this space-time? You can deal with fields defined on the tangent bundle, so you can define the fields here, but also you can define some action here, okay? This action should be integrated both in position and in direction, okay? So in some sense, you are doubling, you have the double of the number of, at least possibly, the double of the number of the degrees of freedom, plus some constraints. But that's a way we can do that. Another way is you define the pseudo-Riemannian metric by considering your Finsler metric and some constraint between the directions or the momentum and the position. So this is called this oscillation method. It's also used in the literature. So what I'm gonna do here is propose a different one. So I wanna define these fields and the dynamics of these fields in the base space using the Finsler metric, but we're gonna do a trick here. The trick is we consider this for momentum and we make this canonical correspondence with the canonical momentum with the derivative. Which derivative we are using? We are using this Cartan derivative in general. Okay? But for a scalar field, it's the usual derivative. So this metric, which will depend on the momentum also, the position and the momentum, will be replaced by an operator which depends on the position, and it's a function of the derivative operator. Okay? So for example, if you consider the D'Alembert operator, so you consider these two derivatives contracted with the metric, but now you have this Finsler metric which depends on the derivative. So you no longer has necessarily a second order operator here, okay? And this, it's very similar to this modified dispersion relation, right? Let me show you once again the modified dispersion relation. Oh, Jesus. It's here. So if you just replace here the momentum operator by the derivative operator, so you end up with this Klein-Gordon equation. Okay. So what you're gonna do is you make this trick. And for the scalar field, for example, all these geometric quantities here are replaced by the Finsler metric. So this k-min-u tensor here is defined by this Finsler metric here, okay? And also this determinant of the metric is replaced by this determinant of the Finsler metric, okay? So this is a very difficult way to solve this, but in rendered space, we can actually have this, the form of these operators, right? So I can replace the expressions here. It's end up with some non-local operators here. You can see, for example, you have this usual kinetic term corrected by these non-local terms here. There is also non-local terms here, okay? But since we are dealing with perturbative Lorentz symmetry violation, so we can make an expansion of this zeta parameter here. And by making this extension, we end up with the usual local Lorentz invariant term plus some Lorentz violating terms here. Some are really interesting because, for example, this first one, this term here has mass dimension 5. In other words, there is more dimension, the mass dimension that usual for renormalized theories. So it's a kind of, here it's a kind of effective theory for this Lorentz violation. Okay. So some of these results, and for other fields, for spinors and for the gauge fields, were also reported recently in this article. Okay. And finally, let's see how this trick works for gravity. So you make the same trick here. You take this Einstein-Hilbert action, okay, with this Riemann tensor. The Riemann tensor here is defined using this Cartan connection, is contracted to form the Ricci scalar using this Finsler metric here, okay, and this determinant of the metric is used for the determinant of the Finsler metric. Why this is interesting? Because if you do so, we are following the principle that this action should be invariant under symmetries which preserved the Finsler metric. That's the point. So the symmetries which preserve the Finsler metric, these are the symmetries of the space-time now, and the Lagrangian should be built using Finsler metric and his derivatives, for example. Okay. So this is the definition from this Riemann tensor. Okay. So if you use this horizontal Cartan connection, we end up with a piece here, which just depends on the position, and corrections which depends on the position and of the momentum. Okay. So when you replace the momentum by the derivative operator and plug here, you end up with this very extensive, very large expression here for the action, okay, in rendered space-time. So you see that we have these non-local terms here, gravitational non-local terms here, and you also have higher derivatives terms here. Okay. So let's just pick up some of them. If you do the same trick, again, if you take some powers of the zeta here, so you end up with the usual Einstein-Hilbert action plus some corrections, which also appears in the standard model extension. So it's a well-known result here. Okay, so summarizing what we have here, we proposed some physics in the Finsler spacetimes, okay, using the Finsler metric with the basis building block. So the symmetries of the spacetime are the symmetries of the Finsler metric. We can use some connections. We can even chain these connections in principle in the tangent bundle to see different symmetries, okay? So these symmetries leads to some kind of Casimir operators, and these Casimir operators, we can see this trick that when you change this momentum in the Finsler metric and now consider the Finsler metric as an operator, now you have a theory for the fields just defined on the basis space. This theory, this action, this Lagrangian is not defined on the tangent bundle. It's defined on the basis space, okay? And this is good. But the price you pay is that now you have non-local terms and high and possibly high derivative terms. Okay, so this is something that we are still analyzing, but I think there is some very interesting perspectives to come up. Okay, so I'd like to thank you all for listening to me. Once again, Gonçalo, for having me.
You are now unmuted.
Thank you, Euclides, for your talk. Very nice discussion or presentation of these Finsler geometries and Rander's Finsler theory. I really enjoyed very much and learned new things, which is very good. That was the purpose of this event. So I see people clapping, but I don't see questions. So maybe I have some questions and doubts. So let me see if I can ask something. Okay, so we are here. Okay. So, for instance, let me see if I understood something right. Okay, because you presented Finsler's geometry and then related this to Lorentz violating extensions or theories. So, but is there a one-to-one correspondence? I mean, any Lorentz violating theory can be written as a Finsler-like theory, or is there a way to break that potential degeneracy?
Okay, I think it depends on which background or which how you see this Lorentz symmetry being the mechanism for the Lorentz symmetry. For example, if you consider this SNE-based Finsler geometries, what you do is you consider this field Lagrangians for the SNE. For example, if you have this vector sector, so you have this background tensors which breaks this Lorentz symmetry, or the graph in the gravitational sector. Okay. Then you consider this point particle limit. With the point particle limit, you consider the modified dispersion relation and the resulting Lagrangian for this point particle limit. And you see that at least in SME models, you always have this Lorentz invariant piece for the Lagrangian plus some corrections. Okay? So in the Finsler function, in the resulting Finsler function, you also have this local Lorentz invariant piece, which I called alpha, plus some corrections in the interval, which depends on the background vectors. So this is the SME way to do that. But I think people in deformed special relativity, I think they do almost the same thing. They start with the modified dispersion relations, and they define this Hamiltonian by taking these Legendre transformations. And dealing with these constraints, they find also this point particle Lagrangian, which is Finsler geometry. So I would say that yes, if you have some model for Lorentz symmetry breaking, and I think you can, and this model provides you some modified dispersion relation, which is a smooth surface, for example, a smooth manifold relating this the momentum and the energy. I think you can always obtain this a Finsler function, which defines some effective geometry which the particle feels this background fields.
Wow.
You are now unmuted.
Okay, thank you. It's really surprising that you can always find a geometric interpretation for those things. So, but anyway, it's been. And have you had a look at the issue of instabilities in these theories? Because I've seen many boxes, many derivatives, higher order derivatives everywhere. So, and this typically develops or introduces instabilities. So, have you looked at some particular example, or is this something that can be somehow controlled?
Yeah, actually, we are still dealing with that. In this article, which I published with Roberto and Carlos 2 years ago, we don't see stability, we don't analyze the stability of this solution, but we analyze the causality of this solution in a very, very simple way. We just see how this, if we start with this high derivative terms, for example, these non-local terms, we see how this, the group velocity grows with some parameters and with respect to the light velocity, speed of light velocity, right? Speed of light. So it turns out that always when the momentum is very, very large, this regime, you always have some superluminal effects. So a particle, even though it's massive, so it's you have some superluminal effects. And this is for the random spacetime. So this is spacetime with a particle feeling this background vector. And this is very, very usual in SME theories. So SME theories, since you have this Lorentz piece here plus some corrections, so for high momentum, you always have this causality in these superluminal problems.
Yeah.
Exactly. But stability we didn't analyze yet.
You are now unmuted.
Okay, thank you. So I think that Albert and Adrian want to comment. So maybe Albert, if you want to turn on your microphone. Please.
Yeah. Well, can you hear me?
Yes, very well.
Well, my question is the following. It is known that if you have non-commutative geometry, the usual one, given rectangular product, we can have mapping between non-commutative coordinates to the usual ones. That is, we replace simple product of non-commutative coordinates by mole product of usual ones. Whether we can have something similar here for the Finsler variable, Finsler coordinates. So whether we can express Finsler coordinates in terms of the usual ones with use of some perhaps other exotic product.
I see. Okay, Albert, thanks for your question. It's very interesting. Yeah, what I think, Albert, is that we are not defining additional coordinates for the space-time here. For example, you still have these x mu coordinates, okay? The additional coordinates is for these velocities, because now, in principle, you are freeing the velocity from the position. You can have any velocity in any position, and you want to describe some kind of Lagrangian geometry. So you want to describe some kind of geometry in the configurational space. You understanding?
Yeah.
So I think what is going on in Finsler space-time is that you have additional degrees of freedom and additional constraints for the geometry, because when you see the geometry now, the natural arena, the natural place to describe this geometry in the tangent bundle, you make this lift, but you have a lot of you have more degrees of freedom, but you have also constraints, as you usually do in Lagrangian analysis, right? So what I really think is not that we are redefining the variables, but we are redefining the space we are dealing with. So maybe there is some kind of, I don't know, there's some kind of to just work on the base space in the first place, just for start, and don't mention the tangent bundle. Okay, by redefining these coordinates, maybe it's possible. But I think the real symmetry is this way to see the things that geometry enables us to see the symmetries which are going on, not on the base space, but in the tangent bundle. You see? But maybe there is some way to mapping the tangent bundle coordinates P to the base space and redefine the base space coordinates. I think maybe it's possible. That's
You are now unmuted.
Okay, so thank you for your answer. So maybe Adrian, you want to ask anything? He wrote in the chat. Okay.
So I wanted to ask whether it is known if, so because you told us that the symmetry group of these theories would be isometries of the metric in the tangent bundle.
Yeah.
Do you know if there are any of these isometries which are isometries of the full metric in the tangent bundle but are not isometries of the space of the spatial part of the metric, in the sense of the metric that lives only in the manifold? So somehow there is a kind of combination in which the transformation properties of the full metric implies that when it acts on objects on the manifold, the iPhone is invariant even though the spatial metric is not.
So I think you are asking if there is some symmetries of the tangent bundle. We are not necessarily symmetries of the metric, the Finsler metric. Is that what you're saying?
Not of the Finsler metric. So if there are any isometries of the Finsler metric, which are not isometries of the spatial part of this metric. If that can be defined. Yes.
Yes, actually, these isometries that I show you, they are isometries of the tangent bundle using the Finsler metric, but they are not isometries of the base space. If you don't use the Finsler metric, if you use this usual pseudo-Riemannian metric, these isometries, which I show you, is not isometries of the pseudo metric. Yeah. So, and that's the beauty of the things, right? Because we can see these hidden symmetries looking at not the basis metric, the pseudo-Riemannian metric, but seeing the Finsler metric instead.
Okay, so in principle, we would have so usual diffeomorphisms would be completely broken in general in this kind of thing.
Yes. Diffeomorphism is not breaking in Finsler geometry. It's not breaking. You can show this. We can show this with Sasaki lift. That this the choice of this new basis is diffeomorphism variant, and also you can have some kind of local deformed Lorentz symmetry in the reference frame, right? In this kind of field lines. Yes, you can define some field lines in the tangent bundle, and the symmetry in these field lines, they are not the symmetry of the basis space using this pseudo-Riemannian metric. Okay, thank you.
Okay, so if there are no more questions, because I don't see any other questions around, so the only thing left is to thank you again, Euclides, for your nice talk, and I hope that you continue with us these days, okay? And enjoy the rest of the talks and lectures. Okay, thank you so much.
Thank you.
Okay, and we are still a bit ahead of the schedule because somehow I started before the planned schedule. So we still have 15 minutes until our next speaker participates, Ulrich Winkers. Ulrich, are you there? I see your name, but I don't know if you are around. It's just to make sure that you will be able to connect.
Yes.
Okay, very good. Okay, so if you don't mind, we can wait until the planned time for your talk in 12 minutes. Okay, is that okay?
I'm so sorry, I didn't catch.
Yeah, if you don't mind, we can wait until 12:45 to start your talk, because it was scheduled at that time. I don't know if someone is planning to attend it, so I don't want to start in advance. Okay, so just hold on for a while, and we will be back in 12 minutes. Okay? Okay, very good. So Silvia will make you presenter again, because I don't have the...
Yes, I did it.
Okay, you already did that. Okay, so Ulrich, you can play around with the buttons just to make sure that everything works well. Okay?
So you can choose or share your screen or upload your presentation. You can see like, okay, that's fine.
Thank you.
see. So we are coming back to the seminar. Where is the seminar? The seminar is here.
You are now unmuted.
Hello. Hello everyone, I'm back. So let me see if I'm broadcasting the correct things. Now it is too small. Okay, it's fine, it's fine. So, Ulrich, thanks for joining us. So let me see if I understood correctly. You are doing your PhD at UCT, right? Yes, very good.
Yes.
And your PhD advisor is?
Is Dr. Alvaro Dombriz.
Okay, very good. So it is time to start. So please go ahead and tell us about focusing conditions for extended teleparallel gravity. Okay, thank you.
Great.
You are now muted.
Well, thank you very much for having me at this talk. I would like to discuss briefly the focusing conditions that arise in a specific class of extended teleparallel gravity theories known as the FT theories of gravity. So I'll mostly discuss some geometric results in the field and also how these can apply to the focusing conditions, specifically the weak and strong focusing conditions in F of T gravity. So I'll first discuss some some standard geometric results in Riemannian and Riemann-Cartan spacetime. So in this talk, I'll only be dealing with non-vanishing curvature and non-vanishing torsion. So there will be no non-metricity tensor. So all the connection, the affine connections that you'll see will be metric compatible. I'll then move on to discuss autoparallels and extremal curves. The distinction between the two is necessary in spacetimes with torsion. And then I will discuss some of the Raychaudhuri equations that appear in the literature, as there is some disputes in the literature about the relevance of some of these equations, specifically with regards to the focusing conditions. So up until that point, that whole discussion will be specific to Riemann-Cartan spacetime. And then we want to apply these results to F of T gravity. So we will then assume the Weitzenberg connection. So we'll have vanishing curvature and non-vanishing torsion to give us the Weitzenberg spacetime. And then we will construct the F of T theories of gravity. And to derive the focusing conditions, we will assume a spatially flat Robertson-Walker spacetime and derive the focusing conditions for a one-parameter dependent congruence of autoparallels. And if time allows, I'll discuss the application of these, or study these focusing conditions for specific F of T functions, specific cosmological models. So it is normally convention to define a spacetime as a tuple, three objects, a differentiable manifold, a metric tensor, and some affine connection. So the Riemannian spacetime upon which GR is built. The affine connection is the Levi-Civita connection. And here I just write the associated connection coefficients that we know from undergraduate GR, as well as the components for the Riemann tensor. And it's worth noting that the Levi-Civita connection is the unique connection that allows for metric compatibility as well as a vanishing torsion tensor. So moving to Riemann-Cartan spacetime, allowing for non-vanishing torsion. The affine connection is referred to as the Cartan connection. And then one can write the connection coefficients in 5. And you can see we can split this into the Christoffel symbols as the connection coefficients associated with the Levi-Civita connection, as well as some torsion tensor terms. And the torsion tensor is just defined as the anti-symmetrization of the connection coefficients. And it is often useful to introduce a tensor field that define in terms of these three torsion tensor terms, so that one can write the Cartan connection coefficients as a purely Riemannian contribution, and a non-Riemannian contribution. And this is through the contortion tensor. So the contortion tensor essentially describes the action of the difference between the two connections, the Cartan connection and the Levi-Civita connection, which are both well defined in Riemann-Cartan space-time. And then here let me just emphasize that then the contortion tensor will then describe a purely non-Riemannian contribution to the connection coefficients. And then I'll just write out the expression for the normal portion Riemann tensor, the total Riemann tensor in Riemann-Cartan spacetime. So by introducing the contortion tensor into this expression, one can also split the Riemann tensor into a purely Riemannian contribution and a non-Riemannian contribution. And it's a useful expression because one can relate the two Ricci scalars through a total covariant derivative and terms that are quadratic in the torsion tensor. And these quadratic terms are often defined as are given its own name, which is the torsion scalar. And it's also useful to define the so-called superpotential, which allows us to write the torsion scalar as a contraction between the superpotential and the torsion tensor itself. And this is quite useful when carrying out a variation of the action that involves the torsion scalar. So now I would like to move on to discuss distinction between autoparallel curves and extremal curves. In Riemannian spacetime, one simply has geodesics, but here I'll refrain from using that definition or using that term. So given some arbitrary affine connection nabla bar in Riemann-Cartan spacetime, we say that some curve with this tangent vector field will be an autoparallel of this connection if equation 15 is satisfied. We will then define, on the other hand, we'll just try and define an extremal curve through extremizing the length integral. If you have 2 points in Riemann-Cartan spacetime, you write down the integral describing the length between those 2 points and you extremize it. And one will get the differential equations in 16. And these actually coincide with the autoparallels of the Levi-Civita connection. The notion of a geodesic will then come in if one has a spacetime such as Riemannian spacetime, where the notions of an autoparallel for the total connection will coincide with the notion of an extremal curve. So in Riemannian spacetime, your total connection is the Levi-Civita connection, and the differential equations are described by an autoparallel of the Levi-Civita connection is exactly the same as an extremal curve, and when these notions coincide, then it's referred to as a geodesic. But yeah, I'll be from now on, I'll just simply refer to autoparallels and extremal curves. So here I would like to now discuss the Ricciardo equations that arise in Riemann-Cartan spacetime, as there's some varying or equations that appear in the literature, all of which are valid. It's more just the application that is of discussion. So if I can just discuss simply the Ricciardo equation that everybody will know from GR, the Ricciardo equation from Riemannian spacetime, one will consider a congruence, a collection of curves, and will have a tangent vector field, and we'll define this tensor field, which is obtained by acting the covariant derivative on this this tangent vector field. And just for a physical interpretation of this field, if we denote eta as the deviation vector, so the vector is going from one curve containing the congruence to its neighbor, and we see that this tensor field actually describes the measure for this deviation vector to be parallel propagated with respect to the Levi-Civita connection. And so then the way this Ricciardo equation is derived is simply by projecting this tensor field into the hypersurface using the spatial metric, decomposing it into a trace part known as expansion, a totally symmetric and traceless part, which is the shear, and a totally antisymmetric part, which is the twist. And this obeys a famous Marshall equation. So this is valid in Riemannian spacetime, but since the Levi-Civita connection is well defined in Riemann-Cartan spacetime, this equation is also still valid in Riemann-Cartan spacetime. But the Levi-Civita connection is not the total connection. The total connection is the Cartan connection. So one can carry out a similar process for the Cartan connection. You can consider a congruence of code generated by the Cartan connection. You can act the Cartan covariant derivative on tangent vector field and define this new tensor field, B tilde. And one can carry out the same process by projecting this tensor field into the hypersurface and then decomposing the tensor into its trace, totally symmetric traceless part and its totally antisymmetric part. And one obtains this Ricciardi equation. And this is exactly what was done by Capriccello et al. That this Ricciardi equation was obtained. Now, of course, this Ricciardi equation is valid and hold true on Riemann-Cartan spacetime. But if one examines the tries to find an interpretation for this field by carrying out a similar process as one does for the Riemannian Ricciardi equation, and considers and applies the Lie derivative, you can see that this tensor field B doesn't completely measure the failure for the deviation vector to be parallel propagated with respect to the total connection. Instead, it is actually this tensor in brackets. It will describe the measure of the failure for this deviation vector to be parallel propagated. And this is exactly what was pointed out by Luth et al. And what they did was they considered exactly this tensor field in brackets, defined it as B circle, and carried out the same process, projected into the hypersurface, do the decomposition, and they obtained this Ricciardi equation. And as was the point of the derivation, was so that when one applies the Lie derivative, one can show that this tensor field does in fact describe the failure for the deviation vector to be parallel propagated with respect to the Cartan connection. So with all of these Ricciardi equations in mind, we need to think about how we will, which Ricciardi equation we will deem relevant to extract the focusing conditions from. Now, if you assume that the test particles will follow extremal curves, which is a reasonable assumption, because of the principle of least action, if you simply write down the length integral for the length between 2 points in Riemann-Cartan spacetime, the application of the principle of least action will give the differential equations associated with an extremal curve. And those coincide, as I mentioned before, with autoparallels of the Levi-Civita connection. So because we are interested in test particles which follow autoparallels of the Levi-Civita connection, we will consider a congruence of curves generated by the Levi-Civita connection. And it will be therefore necessary to consider the tensor field B, which will describe the failure for the deviation vector to be parallel propagated with respect to the Levi-Civita connection. And so because of this, we apply the standard well-known Riemannian Ricciardi equation. And here I've made some simplifications from the equation I stated before, where this term vanishes by assuming that the tangent vector, that we have a congruence of autoparallels of the Levi-Civita connection. And here one can assume a local hypersurface orthogonality, which the Frobenius theorem requires that, implies that the twist will be vanishing. And my apologies, I forgot to mention we are considering time-like curves. So everything, all these tangent vector fields are of norm -1. So then we can follow the, so now that we have this Rashad equation, we can follow the standard process of examining this term. And if one were to require attractive gravity, one can discuss the condition of this being non-negative. And there are two options for that, where G mu nu is just the standard Einstein tensor. One has this option, which is the weak focusing condition in 33, and then one has also the option of the strong focusing condition in equation 34. So now that we have selected the relevant Rashad equation and outlined the weak and strong focusing conditions, which has now been discussed in the context of Riemann-Cartan spacetime. I'd like to now move to applying this to F of t theories of gravity. So in order to construct F of t theories of gravity, one will first need to define the Weissenberg spacetime. This is a specific case of Riemann-Cartan spacetime. We assume that the Cartan connection coefficients are the Weissenberg connection coefficients satisfied by equation 35, and the E and mu are simply the associated tetrads. And in fact, and the whole point of the Weissenberg connection is to ensure that the total Riemann tensor is vanishing. And as opposed to the Levi-Civita connection, which is the unique connection that ensures for metric compatibility and vanishing torsion, the Weissenberg connection is not unique. It is not the only connection that allows for metric compatibility and vanishing curvature. And the choice of this specific, what is referred to as the Weissenberg gauge, is simply that it is in a sense the simplest choice, in the sense that if one were to write down the second Cartan structure equation and require to have vanishing curvature, or write down a vanishing curvature 2 form, I want to find that it's that in the non-holonomic frame, the trivial solution would be to have the connection 1 form be vanishing, and a vanishing connection 1 form implies that the connection coefficients obey this relation. So then F of t theory of gravity is defined as this gravitational action, where t is the torsion scalar that we saw before, on top of the Weissenberg spacetime. And the associated field equations are given in 39. And for us to now discuss the focusing conditions, we move to a spatially flat Robertson-Walker spacetime with a diagonal tetrad construction. And the associated field equations extracted from equation 39 are these field equations. And we have also assumed that the angular momentum tensor is that of a perfect fluid form, and chi is simply the force velocity associated with a co-moving observer. And now to obtain here I would like to discuss the focusing conditions that arise when we consider a congruence of time-like curves that are autoparallels of the Levi-Civita connection, and that are generated as using one single parameter, which is parameter c that I'll mention now. But essentially, we have some velocity in the x direction with respect to the matter field. And so, if we write down the tangent vector field as having this expression, if we want this to satisfy the autoparallel equation as have it that it's an autoparallel of the Levi-Civita connection, it must satisfy equation 46, and then c is our one parameter that will generate the congruence, and when c equals 0, we'll then have a fundamental congruence. And so a useful expression for obtaining focusing conditions will be to write the Einstein tensor. Or since we have vanishing curvature, we can write the Einstein tensors in as purely torsion terms. And we can introduce the f of t function and its derivatives into the right-hand side. And then by carrying out this contraction, one can obtain these weak and strong focusing conditions. In the case where fundamental congruence is considered, i.e. when beta equals 0 has been tried by before by Liu et al. So now if we have focusing conditions, we can study these for specific f of t cosmological models. And for our cosmological models, we consider the case of dust. So we have vanishing pressure, and the energy density has this form. And as for the f of t functions, we require that they satisfy these conditions. That is that the f of t model behaves like TEGR, the teleparallel equivalent of general relativity at the asymptotic limit. And that the first order derivative of the function with respect to the torsion scalar is greater than 0. And this will ensure that the effective Newton's constant will be positive. And to write down these f of t functions is useful to define this dimensionless torsion scalar. Where h0 is simply the present day value of the Hubble parameter. So what we would like to do now is consider these the satisfaction or violation of these conditions for various values of c that generate the congruence of curves. So for example, we can consider a polynomial model. And of course, when sigma equals 0, 1 simply has the equivalent of GR, the teleparallel equivalent of general relativity. And we can see here that as that here it corresponds to c equals 0, so fundamental congruence, c equals 1, and very large c, it's about 10 to the 4. And here we have an increase in the amount of cosmological parameter space where the strong focusing condition is violated. And a similar thing happens for the exponential cosmological model from these figures. Again, an increase in the regional parameter space where the strong focusing condition is violated. And the last model that we consider is a hyperbolic tangent model, from which one cannot extract a standard TEGR with a cosmological constant because of this hyperbolic tangent term. And not only do we find that, yes, there is an increase in the regional parameter space where the strong focusing condition is violated, we also find a region for large C where the weak focusing condition is violated as well. And just to summarize the talk, I emphasize that to derive these, the one parameter, or the focusing condition for one parameter dependent congruence of time-like extremal curves, we use the standard Riemannian-Marchauder equation. We study this for the f of t polynomial exponential hyperbolic tangent f of t models. And we discussed the effect of changing this parameter c. And that concludes the talk. Thank you very much. I'm happy to take any questions, as I haven't been checking the chat room.
You are now unmuted.
Yeah, I have the following
You are now
question.
muted.
In principle, that is because my experience with torsion is relatively small up to now. But the question is the following: whether if we have torsion, we can have non-trivial solutions allowing for causality violation, that is closed time-like curves. that is whether one can have some torsion analog of Gödel solution, for example.
So if I remember correctly, so for example, in if I go to the slides when I wrote down the action for f of t, if we have f of t equals simply the torsion scalar, then simply this is a torsion analog to gr. So for example, if one in gr one has if I remember correctly, the solution, for example, Gödel's universe, which will have closed time-like curves, then that should also have that solution should also appear in the TEGR, the teleparallel equivalence of general relativity. If I imagine then that would be the case. And so I'm not sure, but there may have been. I'm sure maybe it's been studied in the literature that solutions like Gödel's universe also will maybe appear in other f of t models. But ultimately, I'm not entirely certain for beyond f of t equals t.
You are now unmuted.
Okay, question, Albert, is that answer okay for you? So
Yeah.
Oh, very good. Any other question in the public or the chat? There is nothing on YouTube, but there is some delay on YouTube, so if not, one more question. So, Cecilia, can you speak or you want to write? How is your connection today? Okay, micro is broken, so please type your question. Okay. The question is coming.
Не понимаю, она говорит, что у нее микрофон сломался.
So, Ulrich, are you reading the chat? No?
Yes, I see the question.
Okay, so the question is here. So, what happened for other gates different to the W connection, the Weizenbach connection?
Unfortunately, I'm familiar with other gauge choices. I've only really worked with this the trivial solution to the second Cartan structure equation. Yes, I would imagine. I would have to take a guess of it. It's not. Yeah, my apologies. I'm not entirely familiar with other gauge choices. But I imagine if it's simply a gauge choice, then I don't imagine that there should be too much of a change at least at the f of t equals t level. But I wonder then if things will change as if one has a general function of torsion scalar, because it's been found that certain tetrad constructions given a metric you construct a tetrad construction from that. In certain cases, the tetrad may constrain what function will behave like. So I'm wondering if these issues will change with the gauge choice. I'm not entirely certain, but I think it's an interesting question.
Okay, thank you. So anybody else wants to add anything, a comment or a question? Nothing here. If not, thank you again, Ulrich, for your nice talk and addressing the questions. It's been very nice to have you here. I hope you can continue following the talks these days. Okay, so we are reaching the end of the morning session, and so we will have a break now until for 2 hours almost. So at 3 p.m. Central European time, we will be back. Okay, in 1 hour and 45 minutes. Okay.
You are now muted.